Then what we do is we just copy these are called half reactions. So we copy the half reactions off the chart here. So if we look at nitrates up there, so we have nitrate plus 4H plus. And so it reacts in a 1-to-4 ratio, but we don't have to worry about that. Just know we have both species present. Plus 3 electrons yields NO gas plus 2 H2O liquid. So this is a half reaction because we need nitrate and H plus, which we have. Nitrate's coming from sodium nitrate, the H plus is coming from HCl. And we need 3 electrons, which we don't have. Can you go to the chemical store and buy a bottle of electrons? Is that possible? If you go, I'd like a bottle of electrons. Unfortunately, you can't buy a bottle of electrons. We can't buy a bottle. That's because it's going to be too. So this is called a half reaction. A half reaction because the other half has to supply the electrons. And what is the other half? The other half is, there's a problem with the other half though. Iron 2 is a product, not a reactant here. And so what we have to do is we have to flip that. And so we get iron 2 plus goes to iron 3 plus an electron. So this is the other half. The other half is where the electrons are coming from, in this case. And that is, like for example, we can't save the electrons. You can't collect the electrons and save them in a bottle to be used later. But there's a mismatch here because how many electrons do we need? 3, but we are only generating 1. Turns out that's an easy fix. What we're going to do is we're just going to triple the amount of iron. If we triple the amount of iron, then we're going to get 3 times the amount of electrons. And so I just multiply by coefficient 3. And then what I'm going to do is I'm going to just add up the 2 of them to get my net redox reaction. Redox is, we always have to have reduction, we always have to have oxidation. We have to go hand in hand because we can't leave it as half reactions here. And so this is going to go, we'll just add all the reactants together. The 3 electrons cancel out like this. They aren't spectators, but they're consumed. They're produced and consumed. So we'll have nitrate plus 4H plus 3 Fe2 plus. Those are all the reactants. And then we'll just go to products here. NO gas plus 2H2O liquid plus 3 Fe3 plus. Okay, this is the most probable reaction. The most probable reaction is the one between the strongest oxidizer and the strongest reducer. However, if there's no driving force, it just isn't going to happen. So is there a driving force for this reaction? You might say that yes, there's a driving force because what did I form? I formed a gas, and I'm going from stronger acid, H plus, to weaker acid, H2O. So it looks like gas formation and stronger acid to weaker acid should do it for the driving force. Is that okay? No, it's not okay because gas formation and stronger acid to weaker acid is a driving force for what type of reaction? Metathesis in acid-base. But metathesis driving forces do not work for redox reactions. And so we can't use those, even though it'd be nice, we cannot use those for redox. Instead, what do we have to do? Instead, we have to use the driving force for redox reactions. The driving force for redox reactions is stronger oxidizer reducer to weaker oxidizer reducer. And so to do that, we'd like to go to the half reactions here because based on the half reactions, it's easy to see. You're going to set up a competition between the forward reaction and the reverse reaction here. See which direction this is favored. Either the forward, we get reaction, or in the reverse, no reaction. And the way we can do that easily here is to look at the conjugate relationship. If this is the oxidizer, in the forward, then going backwards here, this must be the conjugate reducer. And so in other words, the oxidizer gains electrons going forward. The reducer is going to lose electrons going backwards here. So this is the conjugate. If this is the reducing agent here in the forward direction, then iron 3 must be our oxidizing agent in reverse. And so this lets us assign these. Our oxidizer, nitrate and H+, our reducer, iron 2. Going backwards, NO and H2O, this will be our reducer, and Fe3+ will be our oxidizer. So what's a better oxidizer? The nitrate and H+, or iron 3? So we look there, nitrate and H+, the top, iron 3, is weaker or stronger? You see iron 3, right above oxygen? So is that weaker or stronger? Which one is stronger? Nitrate. Iron 3 is weaker. Because of the conjugate relationship, the reducers are going to be flipped, and therefore iron 2 will be a stronger reducer than NO and H2O. And so we have driving force here. This is driving force. And so we get a reaction. This is a significant reaction because NO is a component of NOx, NOx. Have you heard of NOx? Like if you bring a car for smog test, you know what they test? They test for NOx, oxides of nitrogen, they call it. NO, what's the name of it? NO, what would you call that? You'd call that nitrogen monoxide. Nitrogen monoxide is one of the NOx. There's also dinitrogen monoxide. There's also nitrogen dioxide. There are a whole slew of NOx, NOx. NOx is a component of smog. Smog. There's another name for nitrogen monoxide. Do you know it? The other name for nitrogen monoxide is nitric oxide. Nitrous oxide is N2O. Nitric oxide is NO. Nitric oxide in 1992 won an award. Do you know what award it won? It won Science Magazine's Molecule of the Year. That's what it won. So you look at Science Magazine, the molecule of the year is nitric oxide, NO. You think, why would a molecule that's associated with smog be nominated molecule of the year? Well, it turns out it does have some other important uses. It's a molecule of versatility and importance that has burst onto the scene in many guises. In the atmosphere, it is a noxious chemical, but in the body, in small controlled doses, it is extraordinarily beneficial. And so, anyway, this is what we call a chemical messenger in the body. So it has multiple roles, including, they're saying, for memory and other things. Okay. That's smog, or nitric oxide. So we do see this. So when we look at it, there was significant reaction here. I mean, that's a pretty significant reaction. One, the iron 2 gets converted to iron 3. Iron 2 is green, iron 3 is yellow. And so the color of the solution is going to change from green to yellow. Not only that, we're going to generate a toxic gas, NO gas. And so if you were to mix this up, you've got to be careful because you don't want to breathe the NO gas. Versus the acid-base reaction, it's not that significant, not a significant thing. So, All right, let's see. What we'll do next. Okay, why don't you try one here? Reaction, just chemical reaction. I'm going to do silver plus nitric acid. Do this one, silver plus nitric acid. See what you get.